comes to our sponsors. And now, dear friends, here's Terence Tao. What was the first really difficult research level math problem that you encountered? One that gave you pause, maybe.
Well, I mean, in your undergraduate education, you learn about the really hard, impossible problems, like the Riemann hypothesis, the twin primes conjecture. You can make problems arbitrarily difficult. That's not really a problem. In fact, there's even problems that we know to be unsolvable. What's really interesting are the problems just on the boundary between what we can do relatively easily and what are hopeless. But what are problems where, like, existing techniques can do like 90% of the job, and then you just need that remaining 10%. Um, I think as a PhD student, the Kakea problem certainly caught my eye, and it just got solved, actually. It's a problem I've worked on a lot in my early research. Historically, it came from a little puzzle by the Japanese mathematician Soichi Kakea in like 1918 or so. Um, so the puzzle is that you have a needle on the plane. Or think like like driving like on a road or something, and you want to execute a U-turn. You want to turn the needle around, um, but you want to do it in as little space as possible. So you want to use as little area in order to turn it around. So, but the needle is infinitely maneuverable. So you can imagine just spinning it around its a unit needle. You can spin it around its center, and I think that gives you a disk of area. I think pi over 4. Or you can do a 3-point U-turn, which is what we teach people in their driving schools to do, and that actually takes area pi over 8. So it's a little bit more efficient than a rotation. And so for a while, people thought that was the most efficient way to turn things around. But Bezukovich showed that, in fact, you could actually turn the needle around using as little area as you wanted. So
Hmm.
0.001, there was some really fancy uh, back and forth U-turn thing that you could do, that you could turn the needle around, and in so doing, it would pass through every intermediate direction.
Is this in the two-dimensional plane?
This is in the two-dimensional plane. Yeah, so we understand everything in 2 dimensions. So the next question is what happens in 3 dimensions. So suppose like the Hubble Space Telescope is tube in space, and you want to observe every single star in the universe. So you want to rotate the telescope to reach every single direction. And here's the unrealistic part. Suppose that space is at a premium, which it totally is not.
Yeah.
You want to occupy as little volume as possible in order to rotate your needle around in order to see every single star in the sky. How small a volume do you need to do that? And so you can modify Bezukovich's construction. And so if your telescope has 0 thickness, then you can use as little volume as you need. That's a simple modification of the two-dimensional construction. But the question is that if your telescope is not 0 thickness, but just very, very thin, some thickness delta, what is the minimum volume needed to be able to see every single direction as a function of delta? So as delta gets smaller, as your needle gets thinner, the volume should go down, but how fast does it go down? Um, and the conjecture was that it goes down very, very slowly, like logarithmically, roughly speaking. And that was proved after a lot of work. So this seems like a puzzle. Why is it interesting? So it turns out to be surprisingly connected to a lot of problems in partial differential equations, in number theory, in geometry, combinatorics. For example, in wave propagation, if you splash some water around, you create water waves, and they travel in various directions. But waves exhibit both particle and wave type behavior. So you can have what's called a wave packet, which is like a very localized wave that is localized in space and moving a certain direction in time. And so if you plot it in both space and time, it occupies a region which looks like a tube. And so what can happen is that you can have a wave which initially is very dispersed, but it all focuses at a single point later in time. Like you can imagine dropping a pebble into a pond and the ripples spread out. But then if you time reverse that scenario, and the equations of wave motion are time reversible, you can imagine ripples that are converging um, to a single point, and then a big splash occurs, maybe even a singularity. Um, and so it's possible to do that. And geometrically, what's going on is that there's also light rays. So, like if this wave represents light, for example, you can imagine this wave as a superposition of photons, all traveling at the speed of light. They all travel on these light rays, and they're all focusing at this one point. So you can have a very dispersed wave focus into a very concentrated wave at one point in space and time, but then it defocuses again and it separates. But potentially, if the conjecture had a negative solution, so what that meant is that there's a very efficient way to pack tubes pointing in different directions into a very, very narrow region a very narrow volume. then you would also be able to create waves that start out, there'll be some arrangement of waves that start out very, very dispersed, but they would concentrate not just at a single point, but there'll be a large, there'll be a lot of concentrations in space and time. And and you could create what's called a blow up, where these waves, their amplitude becomes so great that the laws of physics that they're governed by are no longer wave equations, but something more complicated and nonlinear. Um, and so in mathematical physics, we care a lot about whether certain equations in wave equations are stable or not, whether they can create these singularities. There's a famous unsolved problem called the Navier-Stokes regularity problem. So the Navier-Stokes equations that govern the fluid flow for incompressible fluids like water, the question asks, if you start with a smooth velocity field of water, can it ever concentrate so much that like the velocity becomes infinite at some point? That's called a singularity. We don't see that um, in real life. You know, if you splash around water in the bathtub, it won't explode on you, um, or have water leaving at the speed of light or anything. But potentially, it is possible. Um, and in fact, in recent years, the consensus has drifted towards the belief that in fact for certain very special initial configurations of say water, that singularities can form, but people have not yet been able to actually establish this. The Clay Foundation has these 7 Millennium Prize problems, has $1 million prize for solving one of these problems. This is one of them. Of these seven, only one of them has been solved. The Poincare conjecture by Perelman. So the Kekere conjecture is not directly related to the Navier-Stokes problem, but understanding it would help us understand some aspects of things like wave concentration, which would indirectly probably help us understand the Navier-Stokes problem better.
Can you speak to the Navier-Stokes? So the existence and smoothness, like you said, millennial prize problem.
Right,
You've made a lot of progress on this one. In 2016, you published a paper, Finite Time Blowup for an Averaged Three-Dimensional Navier-Stokes Equation.
right,
So we're trying to figure out if this thing usually doesn't blow up,
right.
but can we say for sure it never blows up?
Right. Yeah. So yeah, that is literally the $1 million question. Yeah. So this is what distinguishes mathematicians from pretty much everybody else. Like if something holds 99.99% of the time, that's good enough for most, for most things. But mathematicians are one of the few people who really care about whether every like 100%, really 100% of all situations are covered by yeah. So most fluid, most of the time, water does not blow up, but could you design a very special initial state that does this?
And maybe we should say that this is a set of equations that govern in the field of fluid dynamics,
Yes.
trying to understand how fluid behaves, and it's actually turns out to be a really complicated. Fluid is
Yeah.
extremely complicated thing to try to model.
Yeah. So it has practical importance. So this Clay price problem concerns what's called the incompressible Navier-Stokes, which governs things like water. There's something called the compressible Navier-Stokes, which governs things like air. And that's particularly important for weather prediction. Weather prediction, it does a lot of computational fluid dynamics. A lot of it is actually just trying to solve the Navier-Stokes equations as best they can. Um, Also gathering a lot of data so that they can initialize the equation. There's a lot of moving parts, so it's a very important problem practically.
Why is it difficult to prove general things about the set of equations, like it not blowing up?
The short answer is Maxwell's demon. So Maxwell's demon is a concept in thermodynamics. Like if you have a box with two gases in it, oxygen and nitrogen, and maybe you start with all the oxygen on one side and nitrogen on the other side, but there's no barrier between them. Right? Then they will mix, and they should stay mixed. Right? There's no reason why they should unmix. But in principle, because of all the collisions between them, there could be some sort of weird conspiracy like maybe there's a microscopic demon called Maxwell's demon that will, every time a oxygen and nitrogen atom collide, they will bounce off in such a way that the oxygen sort of drifts onto one side and the nitrogen goes to the other, and you could have an extremely improbable configuration emerge, which we never see, and statistically it's extremely unlikely, but mathematically, it's possible that this can happen, and we can't rule it out. And this is a situation that shows up a lot in mathematics. A basic example is the digits of pi, 3.14159, and so forth. The digits look like they have no pattern, and we believe they have no pattern. On the long term, you should see as many ones and twos and threes as fours and fives and sixes. There should be no preference in the digits of pi to favor, let's say, 7 over 8. But maybe there's some demon in the digits of pi that like every time you compute more and more digits, it sort of biases one digit to another. And this is a conspiracy that should not happen. There's no reason it should happen, but there's no way to prove it with our current technology. Okay, so getting back to Navier-Stokes, a fluid has a certain amount of energy, and because the fluid is in motion, the energy gets transported around. And water is also viscous. So if the energy is spread out over many different locations, the natural viscosity of the fluid will just damp out the energy and it will go to zero. And this is what happens in when we actually experiment with water. Like you splash around, there's some turbulence and waves and so forth, but eventually it settles down, and the lower the amplitude, the smaller the velocity, the more calm it gets. Um, but potentially there is also a demon that keeps pushing the energy of the fluid into a smaller and smaller scale. And it will move faster and faster. And at faster speeds, the effective viscosity is relatively less. And so it could happen that it creates some sort of what's called a self-similar blow-up scenario, where the energy of the fluid starts off at some large scale, and then it all sort of transfers its energy into a smaller region of the fluid, which then at a much faster rate moves into an even smaller region, and so forth. Um, and and each time it does this, it takes maybe half as long as the previous one, and then yeah, you could actually converge to all the energy concentrating in one point in a finite amount of time. Um, and that scenario is called finite time blow up. So in practice, this doesn't happen. So water is what's called turbulent. So it is true that if you have a big eddy of water, it will tend to break up into smaller eddies, but it won't transfer all the energy from one big eddy into one smaller eddy. It will transfer into maybe three or four. And then those ones split up into maybe three or four small eddies of their own. And so the energy gets dispersed to the point where the viscosity can then keep everything under control. But if it can somehow concentrate all the energy, keep it all together, and do it fast enough that the viscous effects don't have enough time to calm everything down, then this blow up can occur. So there are papers who had claimed that, oh, you just need to take into account conservation of energy and just carefully use the viscosity, and you can keep everything under control for not just the Navier-Stokes, but for many, many types of equations like this. And so in the past, there have been many attempts to try to obtain what's called global regularity for Navier-Stokes, which is the opposite of finite time blow-up, that velocity stays smooth. And it all failed. There was always some sign error or some subtle mistake, and it couldn't be salvaged. Um, so what I was interested in doing was trying to explain why we were not able to disprove finite time blow-up. I couldn't do it for the actual equations of fluids, which were too complicated. But if I could average the equations of motion of Navier-Stokes, so basically, if I could turn off certain types of ways in which water interacts and only keep the ones that I want. Um, so in particular, if there's a fluid and it could transfer its energy from a large eddy into this small eddy or this other small eddy, I would turn off the energy channel that would transfer energy to this one and direct it only into this smaller eddy while still preserving the law of conservation of energy.
So you're trying to make it blow up.
Yeah, yeah. So I basically engineer a blow up by changing the laws of physics, which is one thing that mathematicians are allowed to do. We can change the equation.
How does that help you get closer to the proof of something?
Right. So it provides what's called an obstruction in mathematics. So so what I did was that basically, if I turned off the certain parts of the equation, which usually when you turn off certain interactions, make it less nonlinear, it makes it more regular and less likely to blow up. But I found that by turning off a very well designed set of interactions, I could force all the energy to blow up in finite time. So what that means is that if you wanted to prove global regularity for Navier-Stokes for the actual equation, you must use some feature of the true equation, which my artificial equation does not satisfy. So it rules out certain approaches. So the thing about math is it's not just about finding, taking a technique that is going to work and applying it, but you need to not take the techniques that don't work. Um, and for the problems that are really hard, often there are dozens of ways that you might think might apply to solve the problem, but it's only after a lot of experience that you realize there's no way that these methods are going to work. So having these counterexamples for nearby problems kind of rules out. It saves you a lot of time because you're not wasting energy on things that you now know cannot possibly ever work.
How deeply connected Is it to that specific problem of fluid dynamics, or is this a more general intuition you build up about mathematics?
Right. Yeah. So the key phenomenon that my technique exploits is what's called supercriticality. So in partial differential equations, often these equations are like a tug of war between different forces. So in Navier-Stokes, there's the dissipation force coming from viscosity, and it's very well understood. It's linear. It calms things down. If viscosity was all there was, then nothing bad would ever happen. But there's also transport. That energy from in one location of space can get transported because the fluid is in motion to other locations, and that's a nonlinear effect, and that causes all the problems. So there are these two competing terms in the Navier-Stokes equation: the dissipation term and the transport term. If the dissipation term dominates, if it's large, then basically you get regularity, and if the transport term dominates, then we don't know what's going on. It's a very nonlinear situation. It's unpredictable. It's turbulent. So sometimes these forces are in balance at small scales, but not in balance at large scales, or vice versa. So Navier-Stokes is what's called supercritical. So at smaller and smaller scales, the transport terms are much stronger than the viscosity terms. So the viscosity terms are things that calm things down, um, and so this is why the problem is hard in two dimensions. So the Soviet mathematician Ladyshenskaya, she in the 60s showed in two dimensions there was no blow up, and in two dimensions the Navier-Stokes equation is what's called critical. The effect of transport and the effect of viscosity are about the same strength, even at very very small scales. And we have a lot of technology to handle critical and also subcritical equations and prove regularity. But for supercritical equations, it was not clear what was going on. And I did a lot of work, and then there's been a lot of follow up showing that for many other types of supercritical equations, you can create all kinds of blow up examples. Once the nonlinear effects dominate the linear effects at small scales, you can have all kinds of bad things happen. So this is sort of one of the main insights of this line of work is that supercriticality versus criticality and subcriticality. This makes a big difference. I mean, that's a key qualitative feature that distinguishes some equations from being sort of nice and predictable, and like planetary motion. And I mean, there's certain equations that you can predict for millions of years, and or thousands at least. Again, it's not really a problem, but there's a reason why we can't predict the weather past 2 weeks
Mhm.
into the future, because it's a supercritical equation. Lots of really strange things are going on at very fine scales.
So whenever there's some huge source of nonlinearity,
Yeah.
that can create a huge problem for predicting what's going to happen.
Yeah, and if the nonlinearity is somehow more and more featured and interesting at small scales. Um, I mean, there's many equations that are nonlinear, but in many equations you can approximate things by the bulk. Um, so, for example, planetary motion, if you wanted to understand the orbit of the moon or Mars or something, you don't really need the microstructure of like the seismology of the moon, or like exactly how the mass is distributed. Um, you just basically you can almost approximate these planets by point masses, and just the aggregate behavior is important. But if you want to model a fluid, like the weather, you can't just say in Los Angeles the temperature is this, the wind speed is this. For supercritical equations, the fine scale information is really important.
If we can just linger on the Navier-Stokes equations a little bit. So you've suggested maybe you can describe it that one of the ways to uh, solve it or to negatively resolve it would be to sort of to construct a kind of liquid computer,
Right,
and then show that the halting problem from computation theory has consequences for fluid dynamics. So
right,
show it in that way. Can you describe this
right.
idea?
Yeah. So this came out of this work of constructing this average equation that blew up. So one as part of how I had to do this. So there's sort of this naive way to do it. You just keep pushing. Every time you get energy at one scale, you push it immediately to the next scale as fast as possible. This is sort of the naive way to force blow up. It turns out in five and higher dimensions this works. But in three dimensions, there was this funny phenomenon that I discovered that if you change the laws of physics, you just always keep trying to push um, the energy into smaller and smaller scales. What happens is that the energy starts getting spread out into many scales at once. So you have energy at one scale, you're pushing it into the next scale, and then um, as soon as it enters that scale, you also push it to the next scale, but there's still some energy left over from the previous scale. You're trying to do everything at once, and this spreads out the energy too much. And then it turns out that it makes it vulnerable for viscosity to come in and actually just damp out everything. So, um, So it turns out this direct approach doesn't actually work. There was a separate paper by some other authors that actually showed this in 3 dimensions. So what I needed was to program a delay. So kind of like airlocks. I needed an equation which would start with a fluid doing something at one scale. It would push its energy into the next scale, but it would stay there until all the energy from the larger scale got transferred. Only after you pushed all the energy in, then you sort of open the next gate, and then you push that in as well. So by doing that, it kind of the energy inches forward scale by scale in such a way that it's always localized at one scale at a time, and then it can resist the effects of viscosity because it's not dispersed. Um, so in order to make that happen, yeah, I had to construct a rather complicated nonlinearity, and it was basically like, um, like it was constructing like an electronic circuit. So I actually thank my wife for this because she was trained as a electrical engineer, and she talked about she had to design circuits and so forth. And if you want a circuit that does a certain thing, like maybe have a light that flashes on and then turns off and then on and then off, you can build it from more primitive components, capacitors and resistors and so forth. And you have to build a diagram, and and these diagrams you can sort of follow it with your eyeballs and say, oh yeah, the current will build up here and then it will stop and then it will do that. So I knew how to build the analog of basic electronic components, like resistors and capacitors and so forth, and I would stack them together in such a way that I would create something that would open one gate, and then there'll be a clock and then once the clock hits a certain threshold, it would close it. Kind of a Rube Goldberg type machine, but described mathematically. And this ended up working. So what I realized is that if you could pull the same thing off for the actual equations, so if the equations of water supported computation, so like if you can imagine kind of a steampunk, but it's really water punk type of thing where um, so modern computers are electronic. They're powered by electrons passing through very tiny wires and interacting with other electrons and so forth. But instead of electrons, you can imagine these pulses of water moving at a certain velocity, and maybe there are two different configurations corresponding to a bit being up or down. Probably that if you had two of these moving bodies of water collide, they would come out with some new configuration, which would be something like an AND gate or OR gate. That the output would depend in a very predictable way on the inputs, and like you could chain these together and maybe create a Turing machine, and then you have computers which are made completely out of water. Um, and if you have computers, then maybe you can do robotics, hydraulics and so forth. And so you could create some machine, which is basically a fluid analog of what's called a von Neumann machine. So von Neumann proposed if you want to colonize Mars, the sheer cost of transporting people and machines to Mars is just ridiculous. But if you could transport one machine to Mars, and this machine had the ability to mine the planet, create some raw materials, smelt them, and build more copies of the same machine, um, then you could colonize the whole planet over time. Um, so if you could build a fluid machine, which yeah, so it's a fluid robot, okay, and what it would do, its purpose in life, it's programmed so that it would create a smaller version of itself in some sort of cold state. It wouldn't start just yet. Once it's ready, the big robot configuration of water would transfer all its energy into the smaller configuration and then power down. Okay, and then clean itself up, and then what's left is this newest state, which would then turn on and do the same thing but smaller and faster. And then the equation has a certain scaling symmetry. Once you do that, it can just keep iterating. So this, in principle, would create a blow-up for the actual Navier-Stokes, and this is what I managed to accomplish for this average Navier-Stokes. So it provided this sort of roadmap to solve the problem. Now, this is a pipe dream because there are so many things that are missing for this to actually be a reality. I can't create these basic logic gates. I don't have these special configurations of water. I mean, there's candidates, there's things called vortex rings that might possibly work, but also, analog computing is really nasty compared to digital computing. I mean, because there's always errors. You have to do a lot of error correction along the way. I don't know how to completely power down the big machine so that it doesn't interfere with the running of the smaller machine. But everything in principle can happen. Like it doesn't contradict any of the laws of physics. So it's sort of evidence that this thing is possible. Um, there are other groups who are now pursuing ways to make Navier-Stokes blow up, which are nowhere near as ridiculously complicated as this. They actually are pursuing much closer to the direct self-similar model, which can it doesn't quite work as is, but there could be some simpler scheme than what I just described to make this work.
There is a real leap of genius here to go from Navier-Stokes to this Turing machine. So it goes from what the self-similar blob scenario that you're trying to get the smaller and smaller blob
Mhm.
to now having a liquid Turing machine gets
Right.
smaller and smaller and smaller, and somehow seeing how that could be used to say something about a blow up. I mean, that's a big leap.
So there's precedent. I mean, so the thing about mathematics is that it's really good at spotting connections between what you might think of as completely different problems. But if the mathematical form is the same, you can draw a connection. Um, so there's a lot of work previously on what is called cellular automata. Um, the most famous of which is Conway's game of life. There's this infinite discrete grid, and at any given time, the grid is either occupied by a cell or it's empty. And there's a very simple rule that tells you how these cells evolve. So sometimes cells live, and sometimes they die. And there's, when I was a student, it was a very popular screensaver to actually just have these animations go on, and they look very chaotic. In fact, they look a little bit like turbulent flow sometimes. But at some point, people discovered more and more interesting structures within this game of life. So, for example, they discovered this thing called a glider. So, a glider is a very tiny configuration of like 4 or 5 cells, which evolves and it just moves at a certain direction. And that's like this vortex rings. Yeah, so this is an analogy. The game of life is kind of like a discrete equation, and the fluid Navier-Stokes is a continuous equation, but mathematically they have some similar features. Um, so over time, people discovered more and more interesting things that you could build within the game of life. The game of life is a very simple system. It only has like 3 or 4 rules to do it, but you can design all kinds of interesting configurations inside it. There's something called a glider gun that does nothing but spit out gliders one at a time. Um, and then after a lot of effort, people managed to create AND gates and OR gates for gliders. Like there's this massive, ridiculous structure, which if you have a stream of gliders coming in here and a stream of gliders coming in here, then you may produce a stream of gliders coming out. Maybe if both of the streams have gliders, then there'll be an output stream. But if only one of them does, then nothing comes out.
Mhm.
So they could build something like that. And once you could build and these basic gates, then just from software engineering, you can build almost anything. You can build a Turing machine. I mean, it's like an enormous steampunk type things. They look ridiculous. But then people also generated self-replicating objects in the game of life. A massive machine, a polynomial machine, which over huge period of time, and it always looked like glider guns inside doing these very steampunk calculations, it would create another version of itself, which could replicate.
It's so incredible.
A lot of this was like community crowdsourced by like amateur mathematicians, actually. So I knew about that work, and so that is part of what inspired me to propose the same thing with Navier-Stokes. Which is a much, as I said, analog is much worse than digital. Like it's going to be, you can't just directly take the constructions from the game of life and plunk them in. But again, it shows it's possible.
You know, there's a kind of emergence that happens with these cellular automata. Local rules,
Mhm.
maybe it's similar to fluids, I don't know, but local rules operating at scale can create these incredibly complex dynamic structures. Do you think any of that is amenable to mathematical analysis? Do we have the tools to say something profound about that?
The thing is, you can get these emergent, very complicated structures, but only with very carefully prepared initial conditions. Yeah, so these glider guns and gates and software machines, if you just plonk down randomly some cells and you run the game left, you will not see any of these. Um, and that's the analogous situation with Navier-Stokes again. You know that with typical initial conditions, you will not have any of this weird computation going on. Um, but basically through engineering, by specially designing things in a very special way, you can make clever constructions.
I wonder if it's possible to prove the sort of the negative of like basically prove that only through engineering can you ever
Yeah,
create
yeah.
something interesting.
This is a recurring challenge in mathematics that I call it the dichotomy between structure and randomness. That most objects that you can generate in mathematics are random. They look like random, like the digits of pi. Well, we believe is a good example. Um, but there's a very small number of things that have patterns. Um, but now you can prove something has a pattern by just constructing, like if something has a simple pattern and you have a proof that it does something like repeat itself every so often, you can do that. But um, and you can prove that, for example, you can prove that most sequences of digits have no pattern. So like if you just pick digits randomly, there's something called the low large numbers. It tells you you're going to get as many ones as twos in the long run. Um, but we have a lot fewer tools to if I give you a specific pattern like the digits of pi, how can I show that this doesn't have some weird pattern to it? Some other work that I spent a lot of time on is to prove what are called structure theorems or inverse theorems that give tests for when something is very structured. So some functions are what's called additive. Like if you have a function that maps the natural numbers to the natural numbers, so maybe um, 2 maps to 4, 3 maps to 6, and so forth. Some functions are what's called additive, which means that if you add two inputs together, the output gets added as well. For example, multiplying by a constant. If you multiply a number by 10, um, if you multiply a plus b by 10, that's the same as multiplying a by 10 and b by 10 and then adding them together. So some functions are additive. Some functions are kind of additive, but not completely additive. For example, if I take a number n, I multiply by the square root of 2, and I take the integer part of that. So 10 by square root of 2 is like 14 point something, so 10 went up to 14. 20 went up to 28. Um, so in that case, additivity is true then. So 10 plus 10 is 20, and 14 plus 14 is 28. But because of this rounding, sometimes there's round off errors, and sometimes when you add a plus b, this function doesn't quite give you the sum of the two individual outputs, but the sum plus or minus 1. So it's almost additive, but not quite additive. Um, so there's a lot of useful results in mathematics, and I've worked a lot on developing things like this to the effect that if a function exhibits some structure like this, then it's basically there's a reason for why it's true, and the reason is because there's some other nearby function which is actually um, completely structured, which is explaining this sort of partial pattern that you have. Um, and so if you have these sort of inverse theorems, it creates this sort of dichotomy that either the objects that you study are either have no structure at all, or they are somehow related to something that is structured. Um, and um, in either case, you can make progress. Um, a good example of this is that there's this old theorem in mathematics called Semiretti's theorem, proven in the 1970s. It concerns trying to find a certain type of pattern in a set of numbers. The pattern is arithmetic progression, things like 3, 5, and 7, or 10, 15, and 20. And Andre Semiretti proved that any set of numbers that is sufficiently big, what's called positive density, has arithmetic progressions in it of any length you wish. So, for example, the odd numbers have a set of density 1/2, and they contain arithmetic progressions of any length. So, in that case, it's obvious because the odd numbers are really, really structured. I can just take 11, 13, 15, 17. I can easily find arithmetic progressions in that set. Um, but Zermani's theorem also applies to random sets. If I take the set of all numbers and I flip a coin, for each number, and I only keep the numbers for which I got a heads. Okay, so I just flip coins. I just randomly take out half the numbers. I keep one half. So that's a set that has no patterns at all. But just from random fluctuations, you will still get a lot of arithmetic progressions in that set.
Can you prove that there's arithmetic progressions of arbitrary length within a random?
Yes. Have you heard of the infinite monkey theorem? Usually mathematicians give boring names to theorems, but occasionally
Yeah.
they give colorful names.
Yes.
The popular version of the infinite monkey theorem is that if you have an infinite number of monkeys in a room with each with a typewriter, they type out text randomly. Almost surely one of them is going to generate the entire script of Hamlet or any other finite string of text. It will just take some time, quite a lot of time actually. But if you have an infinite number, then it happens. Um, so basically, the theorem says that if you take an infinite string of digits or whatever, eventually any finite pattern you wish will emerge. It may take a long time, but it will eventually happen. In particular, arithmetic progressions of any length will eventually happen. Okay, but you need an extremely long random sequence for this to happen.
I suppose that's intuitive. It's just infinity.
Yeah, infinity absorbs a lot of sins.
Yeah. How are we humans supposed to deal with infinity?
Well, you can think of infinity as just an abstraction of um, a finite number for which you do not have a bound for. Um, that I mean, so nothing in real life is truly infinite. But you can um, you can ask yourself questions like, what if I had as much money as I wanted? Or what if I could go as fast as I wanted? And a way in which mathematicians formalize that is mathematics has found a formalism to idealize instead of something being extremely large or extremely small to actually be exactly infinite or zero. And often the mathematics becomes a lot cleaner when you do that. I mean, in physics, we joke about assuming spherical cows. Like real world problems have got all kinds of real world effects, but you can idealize, send some things to infinity, send some things to zero, and the mathematics becomes a lot simpler to work with there.
I wonder how often using infinity forces us to deviate from the physics of reality.
Yeah, so there's a lot of pitfalls. So we spend a lot of time in undergraduate math classes teaching analysis, and analysis is often about how to take limits and whether So, for example, a plus b is always b plus a. So when you have a finite number of terms and you add them, you can swap them, and there's no problem. But when you have an infinite number of terms, there are these sort of shell games you can play where you can have a series which converges to one value, but you rearrange it and it suddenly converges to another value. And so you can make mistakes. You have to know what you're doing when you allow infinity. You have to introduce these epsilons and deltas, and there's a certain type of way of reasoning that helps you avoid mistakes. Um, in more recent years, people have started taking results that are true in infinite limits and what's called finitizing them. So you know that something's true eventually, but you don't know when. Now give me a rate. Okay, so such that if don't have an infinite number of monkeys, but a large finite number of monkeys, how long do I have to wait for Hamlet to come out? Um, and that's a more quantitative question. And this is something that you can attack by purely finite methods, and you can use your finite intuition. Um, and in this case, it turns out to be exponential in the length of the text that you're trying to generate. And so this is why you never see the monkeys create Hamlet. You can maybe see them create a four-letter word, but nothing that big. And so I personally find once you finitize an infinite statement, it does become much more intuitive, and it's no longer so weird. Um,
So even if you're working with infinity, it's good to finitize so that you can have some intuition.
Yeah, the downside is that the finitized proofs are just much messier,
Yeah.
and yeah. So the infinite ones are found first, usually like decades earlier, and then later on people finitize them.
So since we mentioned a lot of math and a lot of physics,
Mhm.
what do you use the difference between mathematics and physics as disciplines, as ways of understanding, of seeing the world? Maybe we can throw in engineering in there. You mentioned your wife is an engineer, give it new perspective on circuits.
Right,
So this different way of looking at the world, given that you've done mathematical physics, so you've worn all the hats.
right. So I think science in general is an interaction between three things. There's the real world. Um, there's what we observe of the real world, our observations, and then our mental models as to how we think the world works. Um, so we can't directly access reality. Okay, all we have are the observations, which are incomplete and they have errors. And there are many cases where we want to know, for example, what is the weather like tomorrow, and we don't yet have the observation, and we'd like to a prediction. And then we have these simplified models, sometimes making unrealistic assumptions, spherical cow type things. Those are the mathematical models.
Hmm.
Mathematics is concerned with the models. Science collects the observations and it proposes the models that might explain these observations. What mathematics does is we stay within the model and we ask what are the consequences of that model, what observations, what what predictions would the model make of future observations or past observations. Does it fit observed data? So there's definitely a symbiosis. Um, it's math. I guess mathematics is unusual among other disciplines. Is that we start from hypotheses like the axioms of a model and ask what conclusions come out from that model. Um, in almost any other discipline, you start with the conclusions. I want to do this. I want to build a bridge. I want to make money. I want to do this. Okay, and then you 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 find the path to get there. There's a lot less sort of speculation about. Suppose I did this, what would happen? Planning and modeling. Um, uh, Speculative fiction maybe is one other place, but that's about it. Actually, most of the things we do in life is conclusions driven, including physics and science. I mean, they want to know, where is this asteroid going to go? What is the weather going to be tomorrow? But mathematics also has this other direction of going from the axioms.
What do you think? There is this tension in physics between theory and experiment.
Mhm.
What do you think is a more powerful way of discovering truly novel ideas about reality?
Well, you need both top down and bottom up. Yeah, it's a really interaction between all these things. Yeah, so over time, the observations and the theory and the modeling should both get closer to reality. But initially, and it is, I mean, this is always the case. They're always far apart to begin with. But you need one to figure out where to push the other. So if your model is predicting anomalies that are not picked up by experiment, that tells experimenters where to look. To find more data to refine the models. So it goes back and forth. Um, Within mathematics itself, there's also a theory and experimental component. It's just that until very recently, theory has dominated almost completely. Like 99% of mathematics is theoretical mathematics, and there's a very tiny amount of experimental mathematics. Um, I mean, people do it. Like if they want to study prime numbers or whatever, they can just generate large data sets. And so once we had computers, we began to do it a little bit. Although even before, well, like Gauss, for example, he discovered, he conjectured the most basic theorem in number theory, which is called the prime number theorem, which predicts how many primes that up to a million, up to a trillion. It's not an obvious question. And basically what he did was that he computed, I mean, mostly used, by himself, but also hired human computers, people whose professional job it was to do arithmetic, to compute the first 100,000 primes or something and made tables and made a prediction. And that was an early example of experimental mathematics. Um, but until very recently, it was not. Yeah, I mean, theoretical mathematics was just much more successful. I mean, because doing complicated mathematical computations was just not feasible until very recently. And even nowadays, even though we have powerful computers, only some mathematical things can be explored numerically. There's something called the combinatorial explosion. If you want to study, for example, Zermeri's theorem, you want to study all possible subsets of the numbers 1 to 1,000. There's only 1,000 numbers. How bad could it be? It turns out the number of different subsets of 1 to 1,000 is 2 to the power 1,000, which is way bigger than any computer can currently can enumerate. In fact, any computer ever will ever can enumerate. Um, so you have to be. There are certain math problems that very quickly become just intractable to attack by direct brute force computation. Chess is another famous example. The number of chess positions we can't get a computer to fully explore. But now we have AI. Um, we have tools to explore this space, not with 100% guarantees of success, but with experiment. Like we can empirically solve chess now. For example, we have very very good AIs that can, they don't explore every single position in the game tree, but they have found some very good approximation. Um, and people are using actually these chess engines to do experimental chess. Um, that they're revisiting old chess theories about, when you this type of opening, this is a good type of move, this is not, and they can use these chess engines to actually refine, in some cases overturn, um, um, conventional wisdom about chess. And I do hope that mathematics will have a larger experimental component in the future, perhaps powered by AI.
We'll, of course, talk about that. But in the case of chess, and there's a similar thing in mathematics, I don't believe it's providing a kind of formal explanation of the different positions.
But
It's just saying which position is better or not, and that you can intuit as a human being. And then from that, we humans can construct
yes,
a theory of the
right.
matter. You've mentioned the Plato's cave allegory.
Hmm.
So, in case people don't know, it's where people are observing shadows of reality, not reality itself, and they believe what they're observing to be reality. Is that, in some sense, what mathematicians and maybe all humans are doing? Is looking at shadows of reality? Is it possible for us to truly access reality?
Well, there are these three ontological things. There's actual reality, there's our observations, and our models. And technically, they are distinct, and I think they will always be distinct.
Right.
But they can get closer um, over time. Um, and the process of getting closer often means that you have to discard your initial intuitions. Like, astronomy provides great examples. Like your an initial model of the world is flat because it looks flat. And that it's big. And the rest of the universe, the skies is not. Like the sun, for example, looks really tiny. Um, and so you start off with a model which is actually really far from reality. Um, but it fits kind of the observations that you have. So things look good. But over time, as you make more and more observations, bring it closer to reality, the model gets dragged along with it. And so over time, we had to realize that the Earth was round, that it spins, it goes around the solar system goes around the galaxy, and so on and so forth. And the guy's part of the universe is expanding. Expansion is self-expanding, accelerating, and in fact, very recently in this year or so, there's even the acceleration of the universe itself is there's evidence now that it's non-constant.
And, the explanation behind why that is,
It's
I
catching up.
it's catching up. I mean, it's still, the dark matter, dark energy, or
Yeah.
this
Mhm.
kinda thing.
Yes. We have a model that sort of explains that fits the data really well. It just has a few parameters that you have to specify. Um, but so people say, "Oh, that's fudge factors." With enough fudge factors, you can explain anything. Yeah, but the mathematical point of the model is that you want to have fewer parameters in your model than data points in your observational set. So if you have a model with 10 parameters that explains 10 observations, that is a completely useless model. It's what's called overfitted. But like if you have a model with two parameters and it explains a trillion observations, which is basically yeah, the dark matter model I think it has like 14 parameters, and it explains petabytes of data um, that the astronomers have. Um, you can think of a theory, one way to think about a physical mathematical theory. A theory is it's a compression of the universe, and a data compression. So you have these petabytes of observations. You'd like to compress it to a model which you can describe in 5 pages, and specify a certain number of parameters. And if it can fit to reasonable accuracy, almost all of your observations. I mean, the more compression that you make, the better your theory.
In fact, one of the great surprises of our universe and of everything in it is that it's compressible at all. That's the
Yeah.
unreasonable effectiveness of mathematics.
Yeah, Einstein had a quote like that. The most incomprehensible thing about the universe is that it is comprehensible.
Right, and not just comprehensible. You can do an equation like E equals MC squared.
There is actually some mathematical possible explanation for that. So there's this phenomenon in mathematics called universality. So many complex systems at the macro scale are coming out of lots of tiny interactions at the macro scale. And normally, because of the combinatorial explosion, you would think that the macro scale equations must be like infinitely, exponentially more complicated than the micro scale ones. And they are if you want to solve them completely exactly. Like if you want to model um, all the atoms in a box of air, that's like Avogadro's number is humongous, right? There's a huge number of particles. If you actually have to track each one, it'll be ridiculous. But certain laws emerge at the microscopic scale that almost don't depend on what's going on at the macro scale, or only depend on a very small number of parameters. So if you want to model a gas of you know quintillion particles in a box, you just need to know its temperature and pressure and volume and a few parameters, like 5 or 6, and it models almost everything you need to know about these 10 to 23 or whatever particles. Um, so we have we don't understand universality anywhere near as we would like mathematically, but there are much simpler toy models where we do have a good understanding of why universality occurs. Most basic one is the central limit theorem that explains why the bell curve shows up everywhere in nature. That so many things are distributed by what's called a Gaussian distribution, famous bell curve. There's now even a meme with this curve.
And even the meme applies broadly. There's a
Yeah,
universality to the meme.
yeah, yes, you can go meta if you like, but there are many processes. For example, you can take lots of independent random variables and average them together um, in various ways. You can take a simple average or more complicated average, and we can prove in various cases that these bell curves, these Gaussians, emerge, and it is a satisfying explanation. Sometimes they don't. So if you have many different inputs and they're all correlated in some systemic way, then you can get something very far from a bell curve show up. And this is also important to know when the statistical limit fails. So universality is not a 100% reliable thing to rely on. The global financial crisis was a famous example of this. People thought that mortgage defaults had this sort of Gaussian type behavior that if you ask if you have a population of 100,000 Americans with mortgages, ask what proportion of them will default on their mortgages. Um, if everything was decorrelated, it would be a nice bell curve, and like you can manage risk with options and derivatives and so forth. And